Hello, this is Professor Dan Kerler again with our Calc 3 series. Today we're working on section 15.6, and I'm again very casual, unshaven in my Batavia sweatshirt here representing. I'm trying some new settings here with the tablet as well, recording, so trying to make things a little bit bigger in case you're watching it on your phone. We'll see if that helps. Today we're going to talk about tangent planes and then linear approximation, which actually will kind of be like tangential approximation, tangent plane approximation, but you'll see that in a second. So let's talk about first a tangent plane. So let's start here. From 15.5, we learned for a function of two variables, say z, whoops, where is my pen? Z equals f of x, y. The 2D gradient vectors, which are the partial derivative with respect to x, and then the partial derivative with respect to y, they are orthogonal, right? Perpendicular to all the level curves in 2 dimensions. We also learned that for any function of 3 variables, let's say, whoa, scrolled to the side accidentally. Say w equals capital F of x, y, and z. The 3D gradient vectors, oh gosh, what is happening? I feel like it's because I'm resting my hand on there. I might have to figure out how to disable that setting. So the 3 partial derivatives, those are also orthogonal, and they are orthogonal to the level surfaces. So we're going to use this fact to actually get the derivation for what a level, for what a tangent plane is, the equation for a tangent plane. So suppose we have any explicit function, z equals f of x, y. It can be rewritten as a level surface of a function of 3 variables. We're going to make a function of 3 variables. We're going to let w be f of x, y minus z. So there w is a function of x and y and z. Now, of course, w is equal to 0 because z is equal to f of x, y. So we can consider this a level surface of w. So for this level surface, the gradient of w will be the partial derivative of w with respect to x, the partial derivative of w with respect to y, and the partial derivative of w with respect to z. So if we take the derivative of w with respect to x, that'll be the partial derivative of f with point, and we need a normal vector. So here we have a surface, which is z equals f of x, y, and we have a normal vector. It's the gradient. And so we can do an equation here, the equation of a tangent plane. Let me scroll down here. This, to be clear here, this is at the point x naught, y naught, z naught. So remember the tangent, the equation of a plane, a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0, where the a, b, c is from a normal vector. So we're just going to use the gradient then as our normal vector, the gradient of w, I should say. So we will have the partial derivative of x, or partial derivative with respect to x at our particular point, x naught, y naught. That'll be the a times x minus x naught. The b will be the partial derivative with respect to y at x naught, y naught, times y minus y naught. And then, interestingly here, the z component is just -1, so it's always -1 times z minus z naught, and that's equal to 0. And that is the equation for our tangent plane. If you're making a formula sheet, kind of writing some of these key formulas down, that is definitely one that you will want to make a note of. All right, so next here, what if we have an implicitly defined surface where we have f of x, y, z equal to 0? In this case, what we can do is very similarly here, we'll take the partial derivative with respect to x at x naught, y naught, z naught times x minus x naught plus the partial derivative with respect to y at x naught, y naught, z naught times y minus y naught. And then here, since we have a function of x, y, and z already, it is its own level surface essentially. We would take the partial derivative with respect to z of that implicit, of that function on the left-hand side there. Okay, so let's try this. We have an example here that we're going to do. Find the equation of the tangent plane to the surface at the point 1/2, 11/4. And then we're going to try to find parametric equations that represent the line normal to the surface at that point. Okay, so we have our z, which is a function of x and y. It is 4 minus y squared minus x squared. We need the two partial derivatives evaluated at the point. The partial derivative with respect to x will be -2x. The partial derivative with respect to y, -2y. The partial derivative with respect to x then at 1/2 will be -2 times 1, so that's -2. The partial derivative with respect to y at 1/2 will be -2 times 1/2, so that will be -1. So what this means is that we have our normal vector for our plane, -2, -1, and then it's always -1. You can see the derivation from the previous page. It's always -1. This is a normal vector. Actually, let's word it this way. This is orthogonal to the surface at the point 1/2, 11/4. So now you need a plane, right? You have a point and you need a normal vector, and we have a point, we have a normal vector, so we are good. We would say -2 times x minus 1, minus 1 times y minus 1/2, and then always -1 times z minus 11/4. That's our tangent plane equal to 0. Let's go ahead and clean that up a little bit, just make it look a little bit nicer. -2x plus 2 minus y plus 1/2 minus z plus 11/4 equals 0. Let's see, I guess we could add the 2x, add the y, add the z equals, what do we have? 2 plus 1/2, 5/2 plus 11/4. Oh, can't do that in my head. I mean, I could do that in my head, I guess. 21/4. So that is the equation for our tangent plane. And now it also said, scroll back up here, find the parametric equations representing the line normal to the surface. So if you remember lines normal, or the equation for a line, we need a point. We kind of vectorize it. Is that a word? Make it into a vector plus t times a vector in our direction. So for ours, we'll have the point 1/2 I have one last example in this video. We're going to use the gradient vector to find the equation for the tangent plane of the tangent plane to, we need like, what is that? Preposition? Tangent plane to this particular surface at the point 0, 5, 0. So let's think about this first. X squared plus y squared plus z squared equals 25. If we look at all of the traces, if z is 0, you get a circle, y is 0, you get a circle, x is 0, you get a circle. This is a sphere, radius 5. Might as well use some colors. All right, so we have a circle, radius 5 in the xy plane, circle radius 5 in the xz plane, and then a circle radius 5 in the yz plane. And what we're looking at here, we are looking at the point 0, 5, 0. Let's see, x is 0, so we're out here, 0, 5, 0. And the tangent plane over there, what's a good color for the tangent plane? The tangent plane should just be tangent right at the edge over there. It should just be, what should it be? Y equals 5? All right, so let's see what we get. Okay, what we have here, f of x, y, z equals, what we need to do is we need to get it equal to 0. Now it doesn't really make a huge difference this time because the right-hand side was just a constant. But if there was x and y's on both sides, you do need to get it equal to 0. And then and 0. And then we'll have, let's see, 0 times x minus 0 plus 10 times x minus 5 plus 0 times z minus 0 equals 0. And all we get is, oops, scroll down here, apologies, 10x minus 50 equals 0, or indeed x equals, x equals 5. Did I draw that in the wrong spot? X equals 5? Oh, no. Oh, gosh. I could edit this out, but we'll just leave it in there. Okay, so y equals 5 because I can't remember my plane equation. So that's it. That is the equation for a tangent plane. We did a couple of examples here. I hope those are clear. That is this video. We're going to do one more video from this section about linear approximation and using the tangent plane to approximate the function.